Okay, so today I want to shift gears a bit. So we've looked at objects, and many of you by now have created some of your own objects, and played with those a bit. And I know that some of you in the tutorials have been doing the exercises related to dictionaries in Python. So I want to start talking today about sets and dictionaries in Python. So, can anybody tell me what a set is? Yeah.
Set of unique variables that only have one.
Okay. So, a set, the usual definition, at least given in discrete math textbooks, is something like an unordered collection of distinct items. So, unordered is important. It's a collection, so it usually represents a bunch of things, of distinct items. And in mathematics, sets are really important. So at the beginning of this century, mathematics tried to basically define itself from the ground up using sets. That sort of failed for some very deep reasons, but it's not so important to us today. So what's important to us is that it's a collection of distinct items. And so, well, let's see how you define sets. So you can define sets in a similar way to the way you define arrays. So you can say, for example, S is a set. Notice that it's curly braces and not square braces. And you can list out the elements. So maybe it has 1, 2, and 3. And maybe it has the strings A, B, and C. So this is how I define it. And when I inspect it, this is what I see. So maybe the first thing that you observe there is that things don't appear in there in the same order as they were listed when I defined it. And that's really to highlight this fact that this is an unordered collection. So you can put things into it in some order, but that order is not stored in any way, and that order is not relevant. Sets just reorder themselves in some way that's convenient for them. Okay. So that means that in sets, you don't access things by index. So if I ask for s at 0, I correctly get an error. It doesn't make sense to ask for the 0th item or the first item or the second item. None of those things make sense in a set because they're not in any order, unlike in a list. Okay. So let's try another one. So that shows that they're unordered. And let's try making a set that contains 1, 2, 3, 4, A, B, C, and 1, 2, 3 again. And if I look at that, I get something smaller than what I put in. And that's because this 1, 2, and 3 that I put in here, I put them in twice, so I included them in the set twice, but sets contain distinct objects, so the duplicates disappear. Okay, so great. So they're unordered, and you can't put anything in them more than once. That seems to make them less useful than let's say lists, because lists actually do support order, and you can put things in them. What else can you do to sets? Well, you can add things to them. You can remove things from them. And you can check if something is in a set. So I could ask, for example, is 2 in the set? True. Is 3 in the set? False. Okay. Great. So there you see sets. What's so special about these, or why would we want to use them? It seems like they do less for us than lists. And that's true. They do less than lists. But they do it very, very quickly. And so we'll see, really how quickly in a second. But the reason we use sets are because we want to store a collection of things, we don't care about duplicates, and we want to very quickly support these three operations. Adding things should be fast, removing anything should be fast, and testing if, well, this is actually the most important, testing if something is in a set should be fast. So this isn't true in lists or arrays, whatever you want to call them. In a list, if I make a list of 1,000,000 items, and I ask you if something is in the list, or I ask Python if something is in the list, the only way it has of checking that is by going through the list one element at a time and looking to see, is the first element equal to the thing that I'm asking about? Is the second one? Is the third one? And so on. And that goes until it either finds it or it gets to the end of the list and hasn't found it, in which case it returns false. Okay, and that's a big difference from what happens in sets. Sets are organized in a way that you'll learn about in a second-year data structures course, so you'll learn how they're implemented internally. But they're organized in a way that it doesn't matter how big they are, you can test if something is in a set in constant time. So it doesn't matter if a set contains 1,000 elements, 1,000,000 elements, 1,000,000,000 elements. You can still check if something is in there in time that's completely independent of the size of the set. Almost like magic. So you can have a set that contains everything in the universe, and you can ask in the same amount of time to check if something is in there. It's the same. That takes as long as if the set only contained 10 items, which is exactly or almost completely the opposite of a list, which the time it takes to check if something is in there is exactly related to the number of items in the list. And we saw an example of this, of how important this can be, already in the third lecture, I believe it was. And that was when we started playing around, first time we played around with this dictionary. So remember, we opened the list of words. We read it. We converted it to lowercase, and then we split it. So that gives us a list of 99,171 words. And one of the first games we played was to find the list of all palindromes, and that was really a really simple list comprehension where we said it's W for W in words if, remember what this does? This reverses W, and a word is a palindrome if when you reverse it, it's the same word again. So that very quickly gives us a list of palindromes. There they are. There's 130 of them in this dictionary. And then we tried to up the ante a little bit and said, well, what if we want anonyms? Anybody remember what anonyms were? Yeah, so anonyms are words that if you reverse them, you don't necessarily get the same word back, but you do get a word that is in the dictionary. And so the test then, we call something an anonym if we reverse it, and the result is in the words that we have. Okay. And we did that. It was only changing a few characters of code, and suddenly this thing seems to be in an infinite loop. So it's not actually in an infinite loop, but if we think about it for a little while, what did we say? There were 99,171 words in this list. So what's this code doing? Well, it's going through the list for each word. It's reversing that word, and then it's going through the list again to see if the reversed word is in the list. So what's that? How long is that taking? Or what's a rough estimate of the number of calculations that that's doing? So it has 99,171 words. For each of those, it has to go through the list of 99,171 words again to see if it's in there. And so that's the number of comparisons between words that it's doing. So there's 1,000. So I've told you about sets now, and I've told you that sets are these things that are really fast for doing lookups, for checking if something is in a set. So how can we use a set to solve this more efficiently? Yep.
Instead of doing a square brackets, you just do the curly braces?
Like this?
Yeah. Which would then create a set.
This will create a set, but it's not going to help much. Right, so this is just going to create a set, but to create that set, it's still got to go through exactly the same things. It's going through every word in this thing, the list of words, and it's checking if it's in the list of words. Yeah?
Words into a set first and then do that?
Yeah. So it's into a set. How do we do that? Turns out it's really easy. If you want to turn an array, or in fact anything, into a set, you just do that. So you call the set function on it. That turns it into a set. Okay. And if we look at the length of that word set versus the length of the words, it's a little bit shorter. There's about 600, a little less than 600 entries that disappeared. And that probably has to do with capitalization. So the original list of words, we turned it all into lowercase, but there may have been some that were capitalized and some that were not. When I put those into a set, the duplicates disappear. So there's about 600 duplicates in there. Now, to get our anonyms, we want to look at every word and check if its reverse is in the dictionary. So we have two places where we're using words, here and here. So if I could change only one of them, which one should I change? Yeah. The second one, the one on the right. The one where we're checking if the reverse is in the set of words, or the list of words in this case. And that's because sets support checking if something is in them in a time that's really fast, in fact in a time that's unrelated to the size of the set. So it doesn't matter that there's 99,000 or 97,000 things in this set, it still only takes the same amount of time to check if something is in there. So let's try that, and that's it. That's how quickly it runs at that point. Okay. And there's our list of anonyms. Okay. So big difference there, right? And why is that? Well, we sort of know why this is now. If we redo this rough calculation, we did 99,000 of these lookups. But each lookup now, instead of having to look through a list of 99,000 things, it did whatever it does in its internal representation inside one of these sets. Whatever it does seems to be fast. Maybe it has to look at 5 different things, or it's not really doing something comparable to string comparisons, but you know, it's just 99,000 multiplied by some constant. I don't know what that is. Maybe it's 10. In which case, you know, you're only looking at instead of 9 billion, you're only looking at 991,000. So big difference, a factor of 1,000. Okay. So questions there? Okay. So let's see, let's maybe think about something we could do with this thing. Something we could solve with sets. Yep.
Is it possible to put elements of an array into the set?
Yeah, that's what we did right there. So words was an array, and we just converted it into a set. So there's things you can do with sets. So there's a few operations they support. For example, you can clear it, that will empty it. So now if I look at the word set, it's empty. Like I said, you can add things. And you can remove things. So for example, I can remove, I know deed is in there, so I can remove that. So you can add things, you can remove things, whatever you want to do. All of those operations are really fast. Okay. Let's look at another word exercise. So I have here a file that I got from the Project Gutenberg website. It's Varney the Vampire, or The Feast of Blood by Thomas Prescott Prest. It wasn't really written in January 2005. It's a much older book. The reason it's in the Gutenberg collection is because the copyright is expired on it. But it's for us, the main reason we are interested in it is that it's a really long book. So we can see how long it is. In fact, this is just one of many, many volumes in the Varney the Vampire series. Varney the Vampire, I believe, if you treat the series as a whole book, it's the longest book in the English language. Okay. So it was sold back in the 20s or 30s as pulp fiction. So just books that were super cheap and took a long time to read, kept people entertained before televisions existed. So let's play around with that. Let's just read it. Let's lowercase it. So in this particular volume, there's 332,000 words. There's depends on the page, but there's something like 250 pages, maybe 250 words on a typical pulp fiction page. So it's about 1,300 pages long for volume 1 of 13 or something. So it's a long book. So that's great, 332,000 words. Maybe we can try and learn something about the author of this. For example, we could see how well it's written or how literate the author was by maybe figuring out his vocabulary. So what's your vocabulary? That's how many different words you know. It's not how many words you can write. So how many words do you think are in Varney the Vampire? How many different words?
Is that what book we have?
Yeah.
Say it for me.
Well, there's only 330,000 words words in there, counting all the duplicates. So
10,000. 10,000.
oops. We don't actually want the whole set. We just want the length of the set. 26,914. Close. Let's last name. I think I have a copy of War and Peace on here somewhere. So let's try the same experiment with War and Peace. So War and Peace is by itself, it's just it's one book that stands alone, 566,000 words. Great. What do you think the vocabulary is like? Bigger or smaller?
Bigger.
So you've heard of War and Peace before?
No.
No, really?
32. Yeah.
Let's. So Leo Tolstoy. So you guys have never heard of War and Peace? It's a classic. Everybody should have read it. And so, do you think that better authors have bigger or smaller vocabulary? Bigger, substantially bigger. So 40,000 different words appear in there. To a rough estimate, we'd want to clean this data up a little bit if we were trying to be, if we were running a real contest. So for example, we might want to split, we might want to get rid of things like this punctuation and stuff. But this is still a pretty good estimate. So you want to do a spell check?
Well, yeah, like see if there's see which words match in the code sense, and that's a better indication.
So you want to do the intersection or the
Yeah, the intersection. It's like will dash dash they.
okay. So let's well, I mean, we can clean these up. Well, no, that won't work. Okay, so if you want to take the intersection of these two things, anybody tell me how to figure that out? So I'd like to know the words that are in both of these sets. Yep.
It's just intersection, open brackets, and
Yeah, that's too easy. Yeah. Go away. So how could I make, without just using a built-in, how could I make a set that contains only the words that are in common? Yep.
I guess you could do like this set. I don't know how to go in exactly, but like the set of WP.
So words that are in,
Yeah, words that are in one where they're also in the other.
so a word for W in War and Peace if W is in Barney. Right? So 12,000 words in common. We can inspect those. So one thing that's interesting about sets is it's not easy to look at a little piece of a set. because you can't index it. It's hard to tell it, I only want to see a few of the items. You kind of have to dump the whole thing or do something more sophisticated than that. So there's some of the common words. Yep.
It still has plenty of punctuation attached to it.
Yeah, so that's because both of them have a sentence that finish with a dot. We could try and clean that up, but we won't bother today. It's not the
case then that it could be that the thing that book that was much bigger would have more words, it seems, because it would have more words with certain punctuation next to it.
potentially, yeah. Yeah, they both have a sentence that finishes with captain and a question mark, captain and a semicolon. So captain is popular. Okay. All right. How about if we wanted to do a spell checker? So let's say we wanted to spell check War and Peace or either of these things. So what should we load up?
Microsoft Word.
Microsoft Word, yeah. No. Wrong answer. And do we have enough knowledge to do that? Yeah. Yeah. So we've been playing with that already. Let's see, word set we said was open user dict words, read, lowercase, split. User share dict words. Okay. So suppose we want all of the misspelled words in War and Peace. How do we get that? So misspelled is going to be, let's make it a list. So it'll come in in some order. So it's the list of words for words that are in, and I think it was called WP words. That was the original list of words in War and Peace. And when do we want to include these words? If W is not in the dictionary, which is called the word set. See if that works. So why is that taking so long? Yeah, because word set is not a set, so it's a bad name for that. And that's how quickly it takes if you do it right. So I don't know. We can look at misspelled. It's going to be a big dump of words that don't make sense. So it's all the ones typically with punctuation. You'll also find in there section numbers, copyright mark. Ebooks is not a word that's in my dictionary. Gutenberg-TM. So all things you typically find. Okay. What's that? Yeah, if you want to do it really cleanly, if you want to make this a little bit cleaner, when we loaded the books in, we should have stripped out any punctuation. But I won't bother with that right now. Okay, so already with sets we see, well, there's problems we can solve now, actually really easy ones, that it's easy to express the solution, and if you don't know about sets, they won't run in a reasonable amount of time. And that includes things as simple as a dictionary, as spell checking. There's another category of things we want to learn about today, and that's dictionaries. not these dictionaries that are on my desktop, but in Python they're called dicts. And they're like sets in that they store a set of things that are called keys, but with each key there's some other data associated with it. And so so you think of a dictionary as sort of a two-part thing. There's a set of keys, and when I say set, I really mean set now. Every key is distinct, and then there's a value associated with every key. And there can be, values don't have to be distinct. So let's define one of these things. And one way to do that is to say D is equal to So things seem to come in pairs in a dictionary. There's the left side of the pair, the key, and then the right side, the value. And dictionaries, in many ways, they're a generalization of lists, because you can ask for a particular item in a dictionary, but you don't specify it by its index, you specify it by its key. So at the key, for the key me, there's Pat Morin. For the key you, there's Jeff Goldblum. And for the key him, there's Ryan Gosling. And if you ask for something that's not in there, then you get an error. So some of you are encountering this error in assignment 4. So do you want to know how to fix it? You have to not look in the dictionary for a key that's not there. How do you know if a key is there or not? You use the in keyword. Is her in D? The answer is false. Is him in D? The answer is true. Me, and you. Those are all there, but okay. And similarly, if you say something like for S in D, print S, all that you iterate through are the keys. So remember, D is all of these pairs, but if you iterate over it using a for loop, all you get are the keys. Yep.
What happens if you do like D0, D at 0, you get that one?
No, you get an error. So again, the keys form a set. So the set of keys is unordered. So it doesn't make sense to ask for the 0th key or anything. The keys themselves are the indices in some sense. So, if you want to do something that doesn't make a lot of sense, but certainly allowed, you can simulate a list using a dictionary, because keys can be anything, including integers. So I can say D at 0 equals and now there's just another pair in there where 0 is associated with Pedro Gomez. Right. So if I ask for D at 0, I get that. If I ask for D at 1, so yeah. So there's a couple of things that we're doing now, where we can test if something is in the dictionary, or if a key is in the dictionary. That's a really fast operation. We can, if we know that a key is in the dictionary, we can look it up very quickly. That's a really fast operation. We can add a new key to the dictionary. That's what we just did by doing something like that. So it's just like assigning a value to that key. And we can remove a key from a dictionary, but the way we do that is a little bit funny. and it applies to other things too, but we've never really wanted to do it. You just say you delete it. So, for example, if I want to delete me from the dictionary, I just say delete. And now it's gone. Okay. Okay. So let's think about what you might want to use a dictionary for. Well, you might want to use a dictionary for storing a dictionary, right? That's where the word comes from. It's where the computer science term comes from, is from the term that existed before that. What's a dictionary? It's a big book. There's a list, a set of words that are in that book, and alongside each word is a definition of that word. So, so that's where this comes from, right? The keys in a dictionary are the words themselves, and then the values are the definitions that are tied to them. And just like one of these things, dictionaries, the book dictionary, is organized in a way that it's fast to look up a particular word, right? So why is it fast to look up a word in a dictionary? No, in the book dictionary, yeah.
Because it's alphabetical.
Because it's sorted alphabetically. So the data happens to be laid out in a particular way that's related to the keys. It's not at all related to the definitions, in a way that makes it fast for you to find a particular key. On the other hand, a dictionary is completely useless if you're looking for, there's a word on the tip of your tongue, you know what it means, but you can't remember the word. Well, the dictionary is not helpful for that. You can look through the dictionary and read every one of the 40,000 words that are in there, or however many words are in your dictionary, but it's going to probably take a while before you find that word that happens to be on the tip of your tongue. So it's exactly the same thing here. These dictionaries are organized so that you can look things up by key very quickly, but not so much by value. Okay. So let's play with one of these a little bit and see how we could put something maybe non-trivial into a dictionary. NASDAQ listed. So here's a file I just downloaded. It's a list of NASDAQ stock symbols and the companies and some other data associated with them. So this is a CSV file, and the special delimiter here is this vertical bar. Okay. So NASDAQ listed.txt. And there's one of these on each line. So let's take a look at this thing. So 2,734 stock symbols. And right now, the way we've loaded it up, each one is a string. So what do we do with these kinds of files? We've done it before, at least once. Yep.
Split it up into an array, or
Split them up into arrays. So we could do something like, say, tickers equals line for line in tickers. And we don't just want a copy of this thing. We would like to split the line, and we want to split it at these vertical bars here. Okay, so that breaks it up into a nice, into the nice way that it should be. Now, Um, I don't know, maybe our application, and in fact, well, maybe our application is somebody is interested in looking up stock information, and part of that is they give you a stock ticker symbol and you give them information about the company. So they see that you know, on some board some 4-letter symbol is trending high. They want to know about that company, and so you want to be able to look up that information. So seems like dictionaries are what we want for this, right? We have this key, which is this 4-letter symbol, and then information about the company. So how do we get this into a dictionary? Yep.
You have to make the first word in the list become the key.
Okay. So we want to make the first word in the list become the key. So we want to make a dictionary where the first word in the list is the key. And okay, so let's see if we can do that. Let's say tick to info. Let's make that a dictionary. So it's an empty dictionary. And now we would like to go through this list of 2,734 of these things for T and tickers. So T is going to go through a list of these things. So T is going to take on this value of this array at each time. So now we would like to add this thing. So for example, when T at 1 comes up, we would like to add an entry to our dictionary for the key AAIT, and then I don't know what else we want to put, but maybe the company name. That's the second thing here. So how would we do that? Yep.
Tick to info and bracket.
Yep.
And you put a T, open bracket, 0.
Yep.
Close bracket is equal to T, open bracket, 1.
Yep. Okay. So T at 0 is going to be this thing here, the stock ticker symbol, and T at 1 is going to be the company name. Okay, so let's check this thing. Somebody give me a stock ticker symbol and we'll see if it's in there. None of you trade stocks?
FB.
This seems too short, but we can check. True. Let's see what it is. Facebook Inc. Class A common stock. Any other ones? Goog. GOATS. Nope. AAP is not in there. What's that? TAX? DAX. Nope, not in there.
ASUR?
Assure Software.
PSA.
IPSA? Okay, so this thing seems to do what we want. And if we want, we can just look at the whole thing. It's not that big. There. There's only 2,700 things in there. Okay, so are you convinced that this is a useful thing to have in your tool belt now? Okay, so there's nothing you can do with a set or a dictionary that, and especially dictionary, that you can't also do just with a list and with objects, right? Because if you think about sets, all they support is adding, removing, and checking if something is in there. Yeah, you can do that, all those things with a list too. And if you think about dictionaries, well, they support, adding and removing these sort of pairs of things, which you can also add pairs of things to a list. There's no difficulty with that. And you can check if, there's some pair in your list that the key, the first part of the pair, is in the list. So the only difference is these things are a lot faster. So the book, I find, makes a big deal about how useful dictionaries are for organizing data and mapping keys onto values. Yeah, fine, they're useful for that, but the real point of them is that they're much, much faster than any other way of doing it. Now, there are some drawbacks, and it's that they're not that flexible. So for example, here's something I can't do, or something that doesn't work. It's not there, but we looked, right? Goog was there. What's the problem? Both dictionaries and sets, if you're going to put strings in them or anything else, for example, if you're searching for something, there has to be something that's exactly equal to it in there. So since Goog with all lowercase is not equal to Goog all uppercase, it's not in there. Okay, so that's a source of, that's a strong limitation of these things, because this is, for users anyway, this is maybe not the most common use case for let's say this stock ticker problem. Normally what happens is you've heard about a company, it's called, I don't know, Apple Corporation, and you want to buy some stock or you want to look at the stock, and that means you need to know what its ticker info is, not the other way around. Usually if you know the ticker info, you already know the name of the company. And so, we'd like to do something like this. We might like to have a dictionary that works in the other direction, right? So for example, now if I say info to tick at the Pantry Inc. common stock, did I get something wrong? Oops. Then I get the ticker number for it. Now, does this look particularly useful? No, because you have to know exactly the name of the company. All the punctuation correct, all of the abbreviations correct, this uppercase, lowercase, all correct. And so you have no hope, right? I can't just ask for Google there. So these things have limits. They don't let you do things like fuzzy searches or substring searches. All they can do is look for a key that's exactly the same as the key you're looking for. But let's see if we can do something useful with that anyway. So here's a problem for us to solve. I'm curious again about Varney and War and Peace. So let's try and maybe read Varney a little more carefully. Open. I want to read it. And maybe I want to split it into words. Before that, I want to lowercase it. So let's do that. and equals Barney. And maybe I'd like to strip off any extra punctuation. So I think I can strip. I think strip accepts a list of things I can remove. Or if not, we can do it one at a time and see how that goes. So I want to get rid of the periods. I want to get rid of the semicolons. I want to get rid of the commas. Any other big ones? Question marks. Colons. Varney sounds like it could be scary, so there might be exclamation marks. And let's take a random sample now at 5,000 to 5,100. Okay, that's looking better, right? Yeah? Yep. Go ahead.
Doesn't split if there's no arguments. Doesn't it split it into new lines, not words?
Split does white space if there's no arguments. So white space includes new lines, it includes tabs, it includes spaces, all those things. So that gives you pretty much words, except for this punctuation business. Okay, so that looks pretty good. Now, I want to know more than the vocabulary. So I already know that the length of the set Varney is 18,000, while the length of the book Varney is 330,000. I would like to know what the most common words are. So, what are the most frequently occurring words in this book? So, how do I do that? So what should I use? So we've learned about two things today, sets and dictionaries.
You can have a dictionary that's a key of all the words in Barney.
Yep.
And the value would be how many times the words occur.
Okay, so I want to make a dictionary whose keys are the words and the values are how many times that word appears. So how would I make that? So this is getting complicated now. Maybe this is something that we'll actually have to debug, and so we'll edit it in a. Oops, that's not what I want. Okay, so we've done all that. Now I want to make a dictionary which tells me the frequency of every word in here. So for every word, it maps onto an integer which tells me how many times that word occurs. So how would I go about doing that? I want to do this as efficiently as possible. So if you don't care about efficiency, you can look, for example, in there you go. You can find that list supports a method called count. You give it, in our case, a word, and it'll tell you how many times that word occurs in the list. But that means we'll still have to do it for every possible word. So we can try that if you want. I don't know. Want to try that? Yeah.
Can you convert a set into a dictionary?
Can you convert a set into a dictionary? Probably. Why do you want to do that? Okay, which set do you want to convert into a dictionary? Yeah. Okay, so I have my Varney set. And then what?
Search Barney or search that.
No? Okay, so let's see how we can do this. We want to create a dictionary whose keys are words. So, and we'll call this dictionary freak because it's supposed to count the frequency of everything. And until we figured out exactly what we want, we won't try anything fancy like comprehensions. We'll just do it maybe in the most straightforward way possible. So now I've created an empty dictionary. What next? Yeah.
You have a for loop that says for words in Barney, then say when you get the word, you have to search again inside Barney. But this time, what you do is
Search inside Varney?
yeah.
Okay, well, so we can say something like dict at word is equal to Varney.count word. Like that?
Yes. Okay. Yes. Then after you do that, you have to clear out that word.
You have to what?
You delete the word from Barney so that you don't have to keep searching. So it just cuts down the length of Barney.
Okay, so that would be the same thing as this, right? First turn Varney into a set, and then go through that. Well, it doesn't really turn it. I mean, we want to only go through the words in that set, let's say. So maybe a little bit clearer is to say Varney set is equal to set Varney. So Varney's still a list. So something like that?
Yeah.
Okay. Let's see how that and just for a test, we can ask how often the occurs. Zoom. Oh, it's not dict, it's called freak. So why is this slow? On it. Problem there. The problem is here, you think? let's see. This says it's on line 11, and this is line 11. So there's a mistake in the last line, but that's not going to fix it. We didn't get that far. Mistake is still on line 11, where we say freak of W plus equals 1. Yeah. Yeah, so if we look at the first time through this loop, freak is an empty dictionary. And so then we look up freak of W and add 1 to it, but that doesn't work. And in particular, this is just a shorthand for this. And this is what's killing us here, is this looking up freak of W. Yep.
So we first turn it into, first turn the Varney, the words into a set, fill up the dictionary, and then every time a word repeats itself in the dictionary, we make the thing associated to that word plus 1.
Okay, so it just seems all we're missing now is the fact that the words aren't in the dictionary yet. So the minute we hit our first word, we run into an error. So there's a couple of ways we can deal with this. One is to first just load up the dictionary with all the counters set to 0. And for that, we need to get all of those words in there. Is there an easy way to do that? So what should I put in there? Yeah, so for W in Varney, we could say freak at W equals 0. Q, don't know why Q. So that makes sure that every word that we're going to run into will be in there. So the occurs 17,114 times. We can try an experiment, see if we make this a little faster. Probably not. About the same. Okay, so now we have this program that can tell us how often any word occurs. So give me a word that that should occur often in a vampire book. A vampire book from the 1920s. It occurs 16 times. Maybe there's a variation on the spelling. Nope. Vampire is not even in there. Neither is that. Blood? Yeah, that should be in there, right? 88 times. Not much out of 330,000. She. Sun? Remember, this is from the 1920s. Light. Silver. I guess they didn't kill vampires with silver back then. Cross. Crucifix. Not even. Garlic. No garlic. Cullen is the guy's name? No. Gold occurs 15 times. It. Bite. Vampires bite. Twice. Bit. 28 times. Suck might have been a dirty word back then. Though we know it's 18,000 times or 17,000 times. Okay, so let's turn this around a bit. I mean, now we're at the point where we're just trying to guess, the words that occur frequently, and that's fun. But maybe, if this was a data mining application or a trending application, you don't want to have to guess the words. You'd just like to see the most frequent ones. So let's think about taking this whole thing that we've built. So we've built this frequency array, or frequency dictionary, and now we'd like to maybe turn it around and sort it, but you can't sort dictionaries. But if you could, we would like to sort it by the things that occur the most frequently. So it's time to leave the dictionary world and make something else. So what is something that we can sort? Lists. Lists you can sort. It makes sense to sort a list because things are stored in a specific order. If you sort them, they'll be stored in that order. So let's say we take Varney and we turn it into a list. And what do we put in that list? We'll put in pairs of items. We'll put in W and freak of W for W in, well, now we have lots of choices, but we can say for W and freak. Okay. So let's just take a look at that. Well, we don't even have to run it. We can just look at the first 50 elements. So we've got these pairs in there where we have words, kind of. There's a few bad ones. And spirit tabs. I thought we got, so we missed this one because there's quotation marks. We could have cleaned that up a bit better. Okay, so now we'd like to sort this thing. So let's try. Let's say varneylist.sort. Look at the first 50 elements. Is that what we wanted? No. Right, it's not the first 50 elements that we want, and it's not, well, it's not the last 50 elements either. So we're sorting alphabetically, and that's not what we wanted. But I think so we have pairs of things in this list, and when we sort, it seems to take the first thing in the pair as the thing it sorts by. So we can just reorder those pairs. Frequency first, then the word. So the top 50 words, or let's say 100 words, in Varney the Vampire. There they are. Wrong way. Still not quite right. Where are the most frequent ones? At the end. To the end. Okay. So the is the winner at 17,000. Next is to, and, of, I, that, he, you. No big surprises. Jack, Henry.
Barney.
Yeah, so there's a few names. Bannerworth. That's a lot of Bannerworth. Okay, good. So, and there's Varney, of course. Is that the most frequent person's name? Hopefully.
No, Henry.
So Henry appears more than Varney. Okay. So that's great. We've actually done a fairly big data mining task here. But I'm not that happy about this sorting business. So we kind of had to change what we were doing in order to get the sorting to work right. Right. So we we did something like at this point Varney list dot sort. And to make that work, we had to change the ordering of these things. And even then, it didn't work for us because it gave us the least frequent words first. And so maybe we should look at how we can make sort work for us, because it's something that you end up doing a lot. So let's look up Python list sort. I don't like that one. No. Okay. So this suggests that we can... Well, this suggests a bunch of different ways to do it. Let's try this way. Sort. So say that, what do we want to sort by? We want to sort using this function that takes one argument. In this case, the argument is a pair. And we want to return minus pair at 0. See if that works. Perfect. So the first 50 elements of Varney list are those things. Okay. Do you think War and Peace is any better? Any different? What's that? Less the? Okay, let's see. So we just open, let's do the first 100. So in War and Peace, the is still the winner, and to of it's hard to write without using those words. And Prince, Pierre is a highly featured character. Natasha, Princess. I think I saw Moscow in here. Andrew. Yeah. So so there you go. In a few minutes, you can hack together something that does these kind of data mining statistics things. But the take-home lesson from today is sets and dictionaries, they're fast for looking things up. If you find yourself looking things up inside a list frequently, you're doing something wrong.